Okay, so I believe we're live now. Thank you very much for joining us. I'm Natalie Whitehead. I'm a fourth year PhD student here at the University of Exeter. I'm studying my PhD in metamaterials. The title of my PhD is called Graded Index Magnonics. And I'm going to give you a little bit of an insight into what that means in this next 5-10 minutes or so. So I'm doing my PhD as part of the Centre for Doctoral Training in Metamaterials, which basically means that my PhD is done, I work on my PhD, but I work in a cohort. So we have a group of students who are also studying their PhDs. We listen into each other's talks and we kind of help each other on our research. And basically we're kind of studying for our PhDs together. So it's a really nice way to study for a PhD. What I'm going to be talking to you about today, very briefly, is how I got into studying physics and the research that I've been doing for the past 4 years or so. So, sorry, I think we had a bit of a camera issue there, don't worry. So what made me want to do physics was basically a lot of curiosity. I really enjoy learning about things, and for me, getting to learn about the entire universe is just the most exciting thing I think that you can do. So I had actually a little bit of a strange route into studying physics. I did my A-levels, I did maths and physics and English language. And after my A-levels, I wasn't really sure what I wanted to do, but I did decide actually to go and study engineering. So I became an engineer for about 3 years. I studied part-time in an engineering degree and worked as an engineer. Along the way, I actually realised that engineering is super interesting, but what I really enjoyed most about engineering was actually the more detailed stuff. You know, I really wanted to zoom down into a finer detail and try and understand why things were working, rather than just kind of saying, okay, it works, let's go and make something with it. So I actually decided to transfer over to study physics full-time here at Exeter. I was so inspired by all the amazing lecturers that I spoke to on the open day, and I just thought, this is where I belong. So I did my undergraduate here. I did an MPhys, a 4-year degree in physics, and then I stuck around to do a PhD because I wasn't finished, you know. I wanted to keep learning, and I wanted to just be surrounded by these really intelligent and really interesting people for a bit longer. So what I'm going to tell you about now is the kind of research that I've been doing for the past 4 years. So I'm going to need a little bit of an imagination from you guys, because the stuff that I'm doing is mostly theoretical, so I don't have any experiments. I do a lot of computer modelling and solving equations. So first, to give you an idea of what I'm doing, I'm looking at what are called spin waves. So when I said that the title of my research is Graded Index Magnonics, a magnon is the quasi-particle of spin waves, just in the same way that light has a quasi-particle of a photon. So think of photons for light as magnons are for spin waves. So these spin waves are in a magnet, so we have a magnetic material. Imagine we've got a little thin film of a magnetic material. Now, in there, if you zoom in, you'll be able to see that the magnet actually has lots of little tiny atomic magnets in there. So all the atoms act as if they're magnets. So they have a little north pole and a south pole. So I'm going to say that's the north pole and that's the south pole. So in a magnet, the actual thing that makes it magnetic is that all these tiny atomic magnets are pointing in the same direction. So they're kind of all pointing, say, in this direction. Now, if we give this some energy, such as through a laser, or we might use an external magnetic field, a big magnetic field, we can actually get these little magnets precessing. So they actually precess around their axis like this. It's a bit of a weird kind of motion, because normally in physics we look at a lot of oscillatory motion, that kind of things oscillate like a spring. This is kind of similar, but of course it's precessing around an axis, but it's still an oscillatory motion. So this little tiny magnet is going to affect the magnet next to it, because we know that north poles tend to repel, so do south poles, because of the magnetic field that's around each of these magnets. So this one's going to precess, and it's going to affect the one next to it, and the one next to it, and the one next to it. And as you can kind of hopefully see there, that we're getting a spin wave that moves through the material. Now I'm kind of making this pretty simple. But actually, spin waves act in quite a strange way. So because this magnet is actually going to affect all of its neighbours, not just the one next to it here, but over here, this way, this way, this way, and this way. So it's all really complicated. We get some really interesting effects through studying spin waves. So what I'm going to show you, because I'm kind of oscillating these around with my fingers, I want to show you some of my results from my first paper, which basically just shows that motion, and hopefully it'll make a bit more sense to you. So, bring over my laptop over here, and hopefully Tom can zoom in on that a little bit. So what I'm showing here is a region where the magnetization, these little arrows, are pointing that way over here and this way down here. And what we've done is we've made it so that this arrow rotates around and points in this direction. This region here is called a domain wall for any nerdy magnetism fans out there. So we're going to give this whole thing some energy. So what I'm doing here is I'm applying a magnetic field, and that magnetic field is oscillating around, but it's the same everywhere. And just because of the fact that we've got this region where the magnetization rotates around, just because we have that region that everything's a little bit different in the angles that we're rotating, that acts like a source of these spin waves. And you can see what I mean by a spin wave now, because you can see the little wavefronts moving along here and emitting from this domain wall. So that was one of my results from some of my earlier work. But actually, what I'm doing in most of my work now is taking inspiration from optics and applying that to spin waves. Because optics is the study of light. We're just looking at how light behaves as a wave and the cool things that you can do with it. So in particular, I'm looking at something called the refractive index, which hopefully you're all a bit familiar with. What I want to show you is just a really nice little demonstration of kind of messing around with the refractive index to get some really interesting effects. So I've got a Pyrex dish here, and it's filled with oil. And what I've got as well is another Pyrex dish that's actually submerged in there. And hopefully you'll be able to see that underneath, I'm going to move it up and down just so you can see. It looks as if it isn't there inside the oil, right? Because I've cheated and I've filled that with oil too. Now, we should normally see an interface. We should see that there's some edge to that glass. But because we've been a little bit clever and we've put the oil inside the jar and inside this one too, and because the oil has the same value of the refractive index as the Pyrex, what normally happens is you come up to an interface with a different refractive index and the light bends. So it'll bend as it moves to the interface. That's why we can see the glass here. And then it moves into the oil, okay, and it bends and then it carries on moving straight ahead. Now, since Pyrex has the same value of refractive index as oil, pretty much, we don't see any bending at that interface because we only get a bending of the light when the refractive index is different. So what we're seeing here is basically a little trick because we don't see any bending of the light because the refractive index of the oil and the Pyrex is matched. So this is one of our favourite demonstrations. I do quite a lot of outreach, which means I go into schools or we do festivals, and we show little demonstrations of kind of fun things that we can do with light with the refractive index. So this is one of my favourites. But of course, on a day-to-day basis, I'm not necessarily playing around with oil and refractive indices, but this hopefully is giving you an idea of the kind of things that we can achieve by changing or choosing the right refractive index. So what I'm actually doing in my research for these spin waves is I'm playing around with the refractive index, but I'm doing so in a slightly clever way. So they've done this loads in optics. I'm taking inspiration from optics and I'm trying to apply this to spin waves. So as you can see here, I'm just going to put this down because I'm probably a little bit wobbly there. So this is something that you've seen quite a lot of. If you put a straw, or in this case a pen, into a glass of water, you can see that because the water has a different refractive index to the air, that there seems to be a bending at the interface there. So it looks like this pen is disjointed and it's been bent and curved into the water. Again, this is just because we have two different refractive indices. But in this case, since they're different, we're getting a different bending of the light, which makes them appear as if they're in a different position. what I'm doing in my research is actually taking this idea and making it a little bit smoother. So what we've got here is a step change in the refractive index, which means it goes from one value to another, just in a step. But what we can do, now I'm hoping this is going to work, I've got a big, I'm going to just turn that around there, I've got a big tub here that's full of a sugar water solution. So I put this in a few days ago. It isn't quite working perfectly. We've done some tests this morning, but that's fine. We'll see what it looks like. So I've got some sugar water in here, and what I was hoping, and it's working okay, is that the sugar gradually dissolves into this water. And so there should be what I'm going to call a graded refractive index, which just means that if you were to take little slices through this, that the refractive index would be very different here to here, but not very different in each little slice. So we're seeing a very gradual change in the refractive index. And so instead of seeing a really dramatic kind of bending of the light there, we'll actually see a kind of gradual curving of the light. I'm going to show you what I mean. I'm going to get the lights turned off, and thank you very much. What I'm going to do is I'm going to shine my laser pointer in here. I hope this works, and we might need to zoom in a little bit. So I'm going to send my laser pointer in there, and as I curve it down a little bit, you should see just at the edge there, can you see that that's not entirely a straight line, it's just bending down just at the edge. I hope you can see that all right, but what I kind of can see from here is that the light is going in pretty much a straight line. It encounters this region down here where the refractive index gradient is quite strong. So it actually bends downwards towards that end. So you can probably just about see that, and if I was to move that in as well, you can see that it's just about curving in. If I was able to get the graded index really strong there and get a really nice graded index all the way up, we should see some really nice bending. But of course, we're doing physics, and physics doesn't always work quite perfectly as you want to. So this is a demonstration of a graded refractive index. So I'm actually using these ideas for my spin waves. So what does that mean for these funny little spin waves? Well, they're just waves, remember. So I'm going to show you some results of using a graded index profile, which they've used a lot in optics. It's called the Lüneburg lens. And here we go. Hopefully this will work quite nicely. I'll leave that out the one there. Put this over here. So I've created a lens for these spin waves, and I've done this by changing the magnetization, which basically means that the kind of strength of the magnet gets actually increased towards the middle of this lens, and it's kind of increased in a kind of bowl shape, if that kind of makes sense. So this is the outline of my lens here, and what I'm going to do is I'm going to send a wave into it. So I create a wave at this end, it's going to hit my lens. Now this lens is really clever because it tends to bend the wavefront, as you can just see here. It bends it just in the right way to create a focus at the opposite end of the lens. And it works in any direction, so if you sent one in this way, it would get focused over here and vice versa. So what you can see there is that this little focus point is pretty nice, and it turns out that the amplitude there is about 5 times the amplitude that it started with, which means that all of the energy that was hitting the lens, instead of going straight ahead, it's being brought in and focused to increase the amplitude of this lens. I'm hoping that this will have loads of applications for magnetics, for spin waves, in wave-based computing. So one of the main kind of aims of spin waves and spin wave research is to use spin waves as information carriers in nanoscale circuitry. So at the moment in computers we've got little tiny electrical circuits, and that relies on electrons running along through these little copper wires, for example, and it's transmitting energy. In this case, if we have everything fixed, we're just sending a wave through it. It's called wave-based computing, and we're hoping that spin waves can transfer information, and they should be faster and more efficient than traditional circuits. So that's part of what I'm hoping to achieve from this research, and in this case, you can imagine maybe if you send a wave this way, we want to focus it over there and read it with an antenna. So then we focus the energy that way And the great thing about this lens is that you can also launch a plane wave, which just means that the wavefronts are parallel to each other. You can place an antenna here and send out a wave in any direction you want to. So I think it's got some really cool applications. I think that's probably enough from me, so thank you so much for listening. And if you have any questions, please just post them in the comments, and I'll get back to you. Thank you very much.